Our next goal is to decompose U into subgroups and understand its structure. Let U be Zp star and U1 be 1 plus P times Zp as before. And we consider the subgroup U consisting of elements whose P minus 1's power is identity. Then we have that U is the inner direct product of V and U1. Namely, the intersection of V and U1 is trivial, and their product is U. Moreover, we have that V is a unique subgroup of U, isomorphic to Fp star, the multiplicity group of Z mod Pz. To prove this, we're going to invoke Hensel's lemma. In Sar's book, he took the approach of taking a split short exact sequence and taking the inverse limit. And here we are doing differently, which I believe is more rigorous and formal. Let's recall Hensel's lemma. Now we're going to use this lemma with f taken as x raised to the power p minus 1 minus 1. First, let's look at the reduction of this polynomial in Z mod Pz. We observe that every non-zero element in Z mod Pz is a root of this polynomial. Because every element has order dividing p minus 1 here. Moreover, every element here is also a simple root to this polynomial. This is because if you take the derivative, you get p minus 1 times x raised to the power p minus 2. And this is not divisible by p if you take x equal to integers 1 up to p minus 1. Therefore, the derivative does not vanish here. So we have simple roots. Therefore, by Hensel's lemma, those p minus 1 simple roots can lift uniquely to roots of this polynomial over Zp. And we denote those p minus 1 roots by a1, a2 up to a sub p minus 1. Since they all satisfy that a sub k to the power p minus 1 is equal to 1 in Zp, we have that this collection of p minus 1 elements contained in this V. On the other hand, since this polynomial can have at most p minus 1 roots in Zp, so this set has cardinality at most p minus 1. Hence, they must be equal. And those p minus 1 elements are precisely p minus 1 roots of this polynomial in U. Therefore, this V is indeed a subgroup of U of order p minus 1. But remember, for this proposition, we need to show that V is isomorphic to Fp star. and is a unique subgroup with such property. Why is it so? They are isomorphic because if we consider the reduction map, which we denote by pi, from U to Fp star, sending x to x mod p. We consider this a reduction map. Then, what is pi of v? Pi of v, by what we just obtained, is pi of the set with elements a1 up to a sub p minus 1. And this, by our construction, because those are the leaves of those roots, so the reduction of them are precisely 1 bar, 2 bar, up to p minus 1 bar. So this is precisely 1 bar, 2 bar, p minus 1 bar. And this guy, remember, is Fp star. So this means pi as a group homomorphism, when restricted to V, a subgroup with p minus 1 elements, maps V precisely to Fp star. Therefore, this restriction must be an isomorphism, as this is a group homomorphism from a finite subgroup to another finite group, and they have the same cardinality. Because it is a surjection, this must be a bijection, so this must be an isomorphism. This verifies this claim. And now let us show that V is a unique subgroup of U isomorphic to Fp star. This is also obvious. If V prime is any subgroup of U that is isomorphic to Fp star, then any element in V prime must have an order dividing p minus 1. So, by definition, this V prime must be contained in V. On the other hand, because this is isomorphic to Fp star, so this guy must have cardinality precisely equal to p minus 1. And V has a cardinality p minus 1. So they must be equal. And this verifies the second claim. Finally, let us show that this U is the inner direct product of V and U1. We will begin by showing that the intersection of V and U1 is trivial. Indeed, any element in U1, which by definition is 1 plus Z times Zp, has a representation 1 plus P times X for some X in Zp. Suppose this guy is not equal to 1. Then X is not equal to 0. We will show that if we raise this 1 plus px to the power p minus 1, it is not equal to 1. Therefore, 1 plus px in this case cannot be in V. How do we show this? Indeed, we suppose that x is equal to p raised to the power m times u, where p does not divide u. Then 1 plus px raised to the power p minus 1 is equal to 1 plus p raised to the power m plus 1 times u raised to the power p minus 1. And this, by the binomial theorem, is 1 plus, second term is p raised to the power m plus 1 times p minus 1 times u. And the rest is represented by p raised to the power 2m plus 2 times r, where r is in Zp. Now, because p does not divide u, and p is also coprime to p minus 1, so p does not divide this part, which means p raised to the power m plus 2 does not divide the whole thing. But p raised to the power m plus 2 still divides this. Therefore, if we project this element to z mod p raised to the power m plus 2, z, we'll get what? This is a projection onto the m plus 2's component of an infinite vector in Zp. And we are going to apply this projection to 1 plus px raised to the power p minus 1. And this, by our discussion, is 1 plus modulo p raised to the power m plus 2. And this guy is not congruent to 1 modulo p raised to the power m plus 2. This tells us this guy cannot be equal to 1 in Zp, because otherwise all components of this must be equal to 1 in Zp. In particular, this component. Hence, 1 plus px raised to the power p minus 1 is not equal to 1 in Zp. So their intersection must be trivial. Finally, we're going to show that u can be written as a product of v and u1. Indeed, for any u in u, under the reduction, which we denote by pi, from u to fp star, this is then x to x modulo p. Pi of u is an element in fp star, and therefore it has a unique lift, which we denote by v in this capital V. This means the reduction of v is also equal to pi of u, which means pi of v is same as pi of u. So pi of uv inverse, v is invertible because v is a subgroup of u. Pi of uv inverse is equal to 1. So uv inverse is in kernel of pi. But what is the kernel of pi? If you look at this, what is mapped to the identity element here? It is precisely the elements 1 plus p times something. When you take the reduction, you get precisely 1. But what is this? This is precisely the definition for U1. So this is U1. Hence, UV inverse is equal to some U1 in U1. So we get U equal to V times U1. It doesn't matter which one goes first, because this is an abelian group. And this finishes the proof of the proposition 7 in Sarah's book. I think this proof is more formal and rigorous than the original proof he gives. This proof is also indicated in his remark after this proposition. But I want to write a full proof for that remark. In literature, this group V is referred to as a group of multiply representative of the elements of P star. As an immediate corollary to proposition 7, we have that the field of p-adic numbers, Qp, contains the p-1 root of unity. This is simply because this V, which is the subgroup U, is elements whose p-1 power is equal to 1. And this is contained in Zp, and is in turn contained in Qp. Because Qp is by definition the field of fractions of Zp. And we have proved in the previous proposition that this is isomorphic to P star. So in particular, the generator of this group, which is the p-1 root of unity, is contained in Qp.